Hi everyone, I am Charles Laroche, PhD student working between GoPro and MAP5 laboratory from Université Paris-Cité. And I'm going to present our work entitled FastEM, a diffusion model for blind inverse problems with applications to deconvolution. This is joint work with Andrés Almansa and Coupeté. The main goal of our work is to do image deblurring. We suppose that our blurry observation comes from a clean image, X, that has been degraded by a blur operator H, plus some additive Gaussian noise. We suppose the blur to be uniform, which means that our blur operator H is going to be a convolution. In this work, we do blind deconvolution, which means that we want to recover both the clean image X and the convolution kernel H using the blurry observation Y. As a starting point, we noticed a growing interest in the field of diffusion models to solve inverse problems. Those models work for many degradations and have shown impressive restoration quality. They can also be used to model the posterior distribution since they can generate multiple samples from a single observation. DGRM, DPS, and PyGGM are examples of just such models. The problem with those methods is that they are non-blind, which means that they need the degradation as input, limiting their use in real-world applications. Coming back to our inverse problem, we start with the kernel estimation problem, which means that we try to recover the blur kernel from the blurry image. We use the maximum a posteriori on the blur kernel and marginalize on the clean image X we also want to recover. As such, this maximum a posteriori is intractable, so we use the expectation-minimization algorithm to compute it, and more specifically, its stochastic version that uses samples from the posterior to approximate the step. The step reduces to evaluating the log likelihood by drawing samples from the posterior distribution. However, we previously mentioned the impressive performances of diffusion models for this task. The idea for our algorithm is to use a diffusion model to approximate this step. Following this approximation, the M step reduces to a kernel estimation problem given a blurry image and multiple corresponding clean images. In our paper, we propose to solve this kernel estimation problem using a deep plug-and-play version of half-quadratic splitting. Half-quadratic splitting algorithm splits the optimization problem into a data fitting step that deconvolves the image and a regularization step that removes the artifacts introduced during the deconvolution process. The idea behind plug-and-play algorithm is to use pre-trained deep denoisers as regularization on usually the space of natural images. Here, we pre-train a Gaussian denoiser on the space of blur kernels to obtain a regularization on the space of blur kernels. During our experiments, we observed that using a regularization helps to have a kernel estimation model more robust to noise. Finally, the proposed diffusion EM algorithm iterates between drawing samples from a diffusion model given the current blur kernel estimation and a M step that estimates the blur kernel given the current samples from the diffusion model. The problem with this approach is that we have to run the diffusion model for multiple steps, and diffusion models are already long to run. To overcome this issue, we would like to inject the EM iterations directly inside the diffusion process, so that we only run the diffusion model once. To do so, let us come back to the definition of a diffusion model. The idea of a diffusion model is to progressively add noise to an input image until it is only Gaussian noise. By reversing this process, we can sample from the target distribution using Gaussian measurements. Song has formalized this process with the following forward stochastic differential equation. One interesting property of that forward SDE is that its reversed version is explicit. To compute the reversed SDE, you only have to be able to compute the score of the target distribution at time step t. In practice, the score function is approximated using a gradient Gaussian denoiser. In the case of posterior sampling, our target distribution is no longer the distribution P of x, but the posterior distribution, and its score can be decomposed using the Bayes rule as an unconditional score you can use from any diffusion model repository you like, and a guidance term that corresponds to the gradient of the log likelihood. The diffusion process for posterior sampling does not differ too much from generative diffusion models. The main difference is that it uses the current approximation of the denoised xt, which corresponds to x0 hat in our algorithm, to compute the guidance term. The rest of the algorithm is just computing the conditional score using both the unconditional score on the guidance term and a diffusion update, like DDPM for example. To inject the EM algorithm into the diffusion process, we use the fact that the current denoised image x0 hat can be used as an approximation of the posterior distribution. Running several diffusion models in parallel, we can obtain several samples from this approximated posterior. Using those samples, we run the EM step from the expectation-minimization algorithm as previously. In our algorithm, there are two key aspects. The first one is that the distribution of x0 hat progressively converges to the posterior distribution as t tends to 0. So our approximation is getting better and better through the diffusion. The other key element is that in comparison to classical diffusion process for posterior sampling, estimating the kernel adds one line of code and negligible runtime. So basically we design a blind diffusion model that is nearly as fast as its non-blind version. Here is the overall architecture of the FastEM algorithm. The model alternates between a score network, the EM step, and a diffusion step. As you can observe, both the quality of the kernel and the restored image are refined through the iterations. We tested our method on the widely used FFHQ dataset, using a pre-trained denoiser for the unconditional score. We implemented our model on top of DPS and PyDDM diffusion models, which are state-of-the-art non-blind diffusion models. Our model reached the best results on the reference metrics and kernel estimation, and second best on the no-reference metrics. This is mostly because our model targets the map, while blind DPS, which is a diffusion-based method, tries to approximate the full posterior. We can also notice that fast diffusion EM is both faster and of better quality than the classical diffusion EM. Our visual results confirm the quantitative analysis. Traditional methods and deep learning methods fail to handle large blur kernels and noise. Blind DPS produces impressive results, but tends to add some artifacts, like in the second picture, and it does not produce accurate kernel prediction. Our method produces sharp restoration and good quality kernel estimation. To conclude, in our article, we proposed a blind deconvolution algorithm based on the expectation-minimization algorithm that uses diffusion models as image prior and deep plug-and-play regularization for kernel estimation. Our approach achieves state-of-the-art performances for blind deconvolution without significant additive runtime in comparison to non-blind diffusion models. An important source implementation of the code can be found by scanning the QR code.